if we look at our group 1 analysis, in order to separate these, when I precipitate something out, we can dump off the aqueous solution, or we can decant that solution. So at this point, when we added our HCl, we have precipitate number 1 down here, which contains silver chloride and lead chloride, and we have solution number 1 right here, which has our group 2 and our group 3 cations. We're going to save this for a later test. And I should point out that the unknown that you're going to get in your particular experiment only contains group 1, group 2, and group 3 cations. So this solution number 1 contains cations that are in group 2 and group 3. Our precipitate down here is going to contain our group 1 cations. So the first step is, what do we do to our group 1 cation precipitate to be able to separate the lead and the silver and try to identify which one of these is present? Because if you get a white precipitate right here at this step, there's 3 possibilities that you have. One possibility is that there's only silver there. The second possibility is there's only lead. And the third possibility is there's both silver and lead. So what we're going to do is we're going to add water to this solution, or to this test tube, so we create a solution right here. What we're going to do is we're going to heat this test tube. And by heating this, and we touched on this earlier, the lead chloride, that solubility is going to be very, very sensitive to the temperature. So if we heat this, what we'll find is if both of these ions are in the precipitate, our precipitate is going to get a little bit smaller, and this is going to contain silver chloride, and we're going to have lead 2 plus and Cl minus ions in solution. So I'm going to refer to this solution as solution number 2, and the silver chloride we'll call precipitate 2. We're also going to separate each of these. So we're going to decant the solution, which will effectively separate the lead and the silver. So in our test tube right now, we have lead 2 plus ions and Cl minus ions. At this point, the only cation we want in solution is lead 2 plus. And this is an effective way to separate all these out. This is where we have our confirmation step. And in our confirmation step, we would like the confirmation to be a really bold, vibrant color. So if I have lead 2 plus in solution and add potassium dichromate, which is K2Cr2O7, what we find is that we get a lead chromate, or PbCrO4 solid that is going to form. This solid is bright yellow. Back in the day, before we found out that lead chromate has a little bit of toxicity, they used to color school buses this color. Okay? So lead chromate is the bright yellow school bus color. So they actually, I think some school buses still have lead chromate in them. And remember, the toxicity comes from the lead 2 plus ions. So unless the little school kids are going by licking the school bus and putting the lead ions in the solution, they're going to be okay. So don't freak out and call your governor because there's lead chromate on the school buses. Okay? But the thing that we emphasize here, and the reason I point this out, is when I say school bus yellow, most students know what that means. So in the identify step, we want vivid colors. Or we want colors that are not easy to miss. Because students get very frustrated if they lose 6 points because they didn't properly identify if a particular ion was in solution. One other thing that we want, if a precipitate forms, we want it to have a very small KSP. Because remember, when Q is greater than K, a precipitate is going to form. So if our KSP is very, 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 very small, we don't need a large concentration of that particular ion in order to form a precipitate. For lead chromate, the KSP is equal to 1.8 times 10 to the minus 14. This tells us that this is an excellent choice because even with small amounts of lead 2+ in solution, a precipitate will form. And again, we want it to be this bright, bright color. Another thing that we need to make sure that we confirm is that that other white solid that we had is indeed silver chloride. So if we had our precipitate number 1, which we're presuming to be silver chloride, what we want to do is we want to add concentrated NH3 or ammonia. And what we're going to see that upon addition right here, we're going to form a complex ion that is Ag NH3 twice with a +1 charge. I don't know if you remember back to, I believe it was either experiment 6 or experiment 7, where you did this qualitative analysis experiment back in Chemistry 121. This was your actual first introduction to the real project, where you were given this scenario about a painting and an artist or something like that. I don't know if you guys remember that lab. Some of you are shaking your heads. But in that lab, we were introduced to a complex ion. And really the only thing that we told you at that time was a complex ion observation will give us two things. Number one, the precipitate will disappear. Or another way of saying that would be the solid is going to dissolve. Another observation would be that the solution changes color. And in many cases, when we have complex ion formation, they involve transition metals, which is the middle block over here of the periodic table. And we're going to look into the chemistry of transition metals in our next unit and talk about how we can manipulate these color changes. But for now, one of the things that you need to recognize is that when a complex ion forms, there are two things that could potentially happen. Our precipitate could disappear, or our solution could change color. So this particular portion of the lecture served as a foundation and hopefully gave you a little bit of curiosity of, hey, what's going on in here? It certainly did with the chemist back in the day. And as we progress into this unit, we're going to look at 4 particular topics that influence solubility. So the next section is titled Factors that Affect Solubility. And there's 4 main influences that we're going to look at, and I've touched on a couple of them. Number 1 is common ion. And this is solely based on Le Chatelier's principle, and it will be very, very similar to the equilibria expressions that we looked at last quarter. The second effect on solubility, which we touched on to be the separation between the group 2 and the group 3 ions, is pH. The pH of the solution, coupled with the acidity and basicity of the ions in the solution, are going to affect the equilibrium, and they're going to influence the pH. The third influence on solubility is complex ion formation. Like I just said earlier, one of the evidence of a complex ion is that a precipitate will disappear or that it will dissolve. By forming this complex ion, we can really, really influence the solubility and make substances like silver chloride, which does not really want to dissolve, we can force that to dissolve. The last effect that we're going to look at is something called amphoterism, which is kind of a special case of solubility that couples pH effects and complex ion formation. So it's going to be like a combination of the 2 effects. I really, really hate to do this, but there's only a couple minutes of class left, and I think this is an excellent point to stop and to put a break. So we will start class up on Wednesday, and we will talk about the common ion effect, pH effects of solubility, and maybe get into complex ion formation.